Our moon, the Earth's moon, has always played an important role in human history. Ancient philosophers saw the moon as the boundary between the earth and the heavens, and our ancestors observed the moon throughout the night sky to try and understand more about this celestial object. In this video, we're going to be going through the ancient history of the moon, going back as far as 30,000 years ago up until the 20th century, trying to learn as much as our ancestors did about the moon with the little technology that they had. So let's talk about that. Before I get too far into this video, I do want to mention I'm mostly going to be focusing on the scientific and observational discoveries around the moon, rather than looking at the mythology or deities named after the moon. There's quite a bit of information on both sides of this spectrum, so if you would like to learn more about the mythology of the moon, let me know in the comments below. But to begin, before we even get to written history, we have to understand our natural behavior around the moon. Now, there is no doubt whatsoever that the sun has a major influence of life here on Earth. Whether it be plants requiring sunlight in order to grow or create oxygen, and if we look at the other end of the spectrum, seeing how animals can be nocturnal or not, meaning that they're mostly active during the day or night. So it's pretty clear that the sun has a major influence on life. However, the moon also influences natural behavior as well. Now, some marine organisms have something called a circa-lunar clock. A circa-lunar clock is actually helping organisms maintain how often they need to sleep or reproduce for these marine life. And some scientists believe that this is a major influence because the moon impacts the tides of the sea. However, different sea worms or even crabs that have been taken out of the sea, put into aquariums, also show these weird cycles where they're able to keep track with the moon's phases, and their behaviors change depending on that. So it's very interesting to see that there are various reactions to this marine life in terms of where the moon is. To make this more relatable to you as a human, there have been studies that have shown the phase of the moon actually influences your sleeping patterns. So for example, during a full moon, it will take you longer to fall asleep and the overall quality of your sleep will be lower. So the next time you have a bad night's rest or you don't sleep very well, check the phase of the moon and see if that had any influence on it. But speaking of sleeping, prey that usually are active during the night will be less active whenever there's a full moon because it's brighter outside. So because of the prey that are being less active, predators or large predators, for example lions, will typically hunt more often during the day. So it's actually been seen that lions hunt during the day more frequently after a full moon. So if you would think these ancient animals, their behaviors are changing depending on whether or not there's a full moon. So did our ancient ancestors notice this? And this actually leads us to the very first lunar calendar, which was discovered in cave art in France and Germany. In fact, this is the Nation lunar calendar, which was thought to be made in 32,000 BC, or being 34,000 years old. It's very hard to tell that it is a lunar calendar, but you can kind of depict the different phases that they are showing. And again, these drawings could have been off because it could have been cloudy and they are drawing what they saw. It is thought that these calendars would be carved onto bone or antlers that would be easy for hunters to carry to be able to determine what the behavior of the animals they are hunting is. So for example, when they went out hunting for horse, bison, or even mammoth, they would be able to determine what the overall behavior is. And yes, you heard that correctly, mammoth. These calendars were created during the last ice age. We are now going to fast forward by 28,000 years, taking us to the year 4000 BC, where the ancient Egyptians were looking at a lunar solar calendar which was very similar to the Gregorian calendar that we use now. This calendar had either 12 or 13 months that was dependent on how long it took the moon to go around the Earth, as well as how long it took the Earth to go around the sun. But we have to remember these ancient Egyptians didn't know how these orbits worked, but rather were just learning this through their observations in the night sky. Now after the Egyptians' lunar solar calendar, we get to the year 3000 BC, where the Egyptians saw Khonsu as the god of the moon. And Kansu translates directly to traveler, which represents how the moon travels throughout the sky. And if we fast forward another 2,000 years, getting to the year 900 BC, we start to see Greek mythology forming, and they represent Artemis as the goddess of the moon. Now, Artemis is also the goddess of hunting, wild animals, and the wilderness. But does this sound a little familiar? It's strange that they would tie the goddess of the moon with the goddess of hunting, wild animals, and the wilderness. But if we think about it for a second, go back to 31,000 years prior when these ancient humans were using these calendars to help them hunt. They're using the moon as a primary tool in order to get the animal or food that they need. So here we are, 31,000 years in the future from this first lunar calendar created, where the new goddess of the moon is depicted as the goddess of hunting, because they tie these things so closely together. Now, NASA named their new project to go back to the moon Artemis, and it's very fitting because, again, Artemis is the goddess of the moon, but it's also Apollo's sister. So it's looking back to about 50 years ago when the Apollo missions were going to the moon. Now, moving forward to the year 500 BC, we look at the Babylonians, and they are keeping a very active record of solar eclipses, lunar eclipses, and the phases of the moon. Now, with all this information, they were able to determine the different lengths of different kinds of months. But did you know that there are different kinds of months? And when I say different months, I don't mean January versus February, but different kinds of months, how we keep track of the moon around the Earth. Here, let me explain two of the more popular months for you to get a visualization of why these are different. First of all, we have the sidereal month. Imagine the moon orbiting around the Earth, and it starts on the left side. A sidereal month is calculating or basically timing how long it takes to go from that one point on the left side and return exactly to that point. So if you're observing that here from Earth, that would look like basically returning to the exact same point in the night sky. And you might think, well, that's pretty close to a day, but it turns out that the positioning of the moon actually changes just slightly. So it does require a sidereal month to get back to that exact same point. But that doesn't require the phases to be the exact same, and we'll see why in just a second. Now, a sidereal month is 27 days, 7 hours, 43 minutes, and 11.6 seconds long. Now, another kind of month is called a synodic month, which is how long it takes for the sun, earth, and moon to return to the same alignment, or relatively the same alignment. Or you could think about it as how long it takes from one full moon to get back to another full moon. So how long does it take for the phases to return back to the same phase? And this ends up taking 29 days, 12 hours, 44 minutes, and 2.8 seconds. But 29 days, that's 2 whole days longer than the sidereal month. Why is a synodic month that much longer? What exactly does this look like in space? Let's think about these orbits. Again, the sidereal month is pretty easy to understand. All we have to do is time how long it takes the moon to go from that one point and return all the way back, or complete one full circle around the Earth. But for a synodic month, remember, we're looking at how the Earth, moon, and sun align. And the Earth is also orbiting around the sun. So let's watch this unfold. If we go up until the amount of time it takes for a sidereal month, it hasn't aligned yet. It still has to go a little bit further. And this is because how much the Earth has moved in its orbit. So if we continue it on for a couple more days, then it aligns back up again, and thus we have a synodic month, which is why it is longer than a sidereal month. But let's jump back to the Babylonians for a second. Remember, they were 2,000 years before Newton or Kepler, and Newton and Kepler described this orbital motion. So they just had their observations of the moon in the night sky, where it was with respect to the background stars, and what phase it was, or what was the alignment with the sun. And this was the information they had to determine these lengths of these different kinds of months. So how close were they? It turns out when the Babylonians were calculating the synodic month, they were 99.999983% of the right answer. And for the sidereal month, they were 99.999941% of the correct value. That is incredibly close for being 2,500 years ago. I know it's mostly just observation and timing, but that's incredibly impressive that they were able to get those values. In addition to their observations of the moon, they also did a great job measuring the motion of the sun. And with this information, they were able to calculate something called a metonic cycle, which is used to determine when future eclipses are going to happen, both solar and lunar eclipses. So the Babylonians really knew what they were doing in terms of astronomy, even though it was 2,500 years ago. Now in the year 400 BC, about 100 years after these observations by the Babylonians, a Greek philosopher by the name of Anaxagoras made the prediction that the sun and the moon are actually these two rocks, and the sun is emitting light and the moon is only reflecting light. Then in the year 200 BC, a Hellenistic astronomer by the name of Seleucus of Seleucia made the very first observation that the moon influences the ocean's tides. Then around this same time frame, Aristarchus of Samos made the observation that the Earth is about 20 times closer to the moon than it is from the sun. And this observation was one of the very first that tried to determine the distance between the Earth and the moon. However, he was off by quite a bit. The actual value is 400 times, so the moon is 400 times closer to the Earth than the Earth is to the sun. But a much better approximation of the distance between the Earth and the moon would come in the year 100 AD, when Ptolemy estimated that the distance is about 59 times the distance of the radius of the Earth, which in fact the real value is 60 times the distance of the radius of the Earth. So that is very impressive. And the reason that they don't have actual distances like kilometers or miles is because they weren't for sure what the distance of the Earth was. But using trigonometry or a bunch of fancy angles and triangles, they were able to determine how well it was with respect to the size of the Earth. Because they might not know the size of the Earth, but they can get a relative sense compared to how big the Earth is. Now after Ptolemy made these predictions around 100 AD, there weren't that many observations or new discoveries about the moon until the year 1609. Now there were a lot of people that were looking at how the moon reflected light, but there wasn't a lot of an understanding about what actually is happening on the moon, until Galileo was able to look through his telescope and determine that the crescent on the moon isn't perfect. There are mountains and craters and valleys which show that there is actual a topographic region on the moon, or there are different elevations. And with this information, this began a whole new exploration of what the surface of the moon looked like and the near side and how we could actually map it. So about the same time that Galileo was making his observations about the surface of the moon, Kepler was working on his laws of planetary motion. And Kepler's laws of planetary motion helped define what we currently understand as orbits and how spacecraft orbit planets and how planets orbit the sun. All this information was heavily introduced by Kepler's laws of planetary motion. Then about 80 years later, Newton would come about with his laws of motion as well as the law of universal gravity, which would help us understand how exactly the moon orbits around the Earth, and how we can truly explain the motion of the moon without having to rely on all these observations. And these equations that Kepler and Newton developed in the 17th century are still being used today to help us explain the motion of spacecraft, planets, moons, and other types of satellites. At the time of Newton, a lot of the parameters or constants that he used we didn't have a good representation of. Things such as the mass of the Earth or the mass of the moon. We had no idea what these things were. So over the following couple hundred years, many astronomers were keeping track of the different surface structures of the moon, what craters and mountains look like. Different physicists were trying to determine how massive is the moon, how massive is the Earth, and how can we actually use these equations that Kepler and Newton provided with us. And up until the 20th century, there were many observations and new things learned about the moon before we had even sent a spacecraft there, which was incredibly remarkable to think that all of our ancestors throughout all of human history have been fascinated by the moon and have shown us all this interesting information without us even being able to go there.